There we go. Morning. Nice to see those of you who could make it. Is always appreciated, and hopefully you're having a good week if you're watching this video later. So yeah, no, probably well, not everyone, but some people are probably tired because we just finished a project cycle, and unfortunately, the nature of the beast for us is that the end of one project cycle is the beginning of another until the end of the semester. Morning, Cast. Happy to see you as always. So yeah, anyway, I'll be mentioning Project 3 today, which I know is tiresome to hear that there's more projects to do. But we're halfway through them, so uh, happy Halloween, RoboGenko. Nice to see you as always as well. So I'll get the projects graded as soon as I can. I get up very, very, very early on Mondays to try to knock out to get your grades back to you as quickly and efficiently as possible. Um, Morning, Amber Wolf. So anyway, as always happens on the Monday morning after a project, I created all kinds of havoc in people's lives. So I ended up spending about an hour of my morning answering emails for people who didn't know that you could work on the project for the whole month or whatever it was. That's just me being sarcastic. So anyway, I will get to grading the projects as fast as I can, but I do lose a fair amount of time on Monday mornings after projects come due answering emails from people who wait till then to contact me. So I will catch up um, and get through the grading of the ones that I've got as efficiently as possible. Hi, Magenta. Happy Monday. So there you have it. 16 people got them turned in, and I don't remember how many people we have enrolled presently, but that's the bulk of you got something turned in. So yeah, project grades as soon as I can, which means I don't have demos this week because it takes me a while to work through projects and read through code and stuff. I'll do my best. Hopefully before I go to bed tonight, I will get that done. Um, okay. Anyway, so there's that, and apologies in advance because I am going to mention Project 3 today. Which I have tried to make a little easier for you in the sense that the labs are all building up to that spot, and then reusing the techniques that we've been practicing a lot, in part because of Project 2. All right, where are we at? Week 11. So we're finally getting down to kind of the small end of the semester. You guys have 2 projects left. One of them is due just short of 3 weeks from now on November 20th. And then the next one after that will be due the Sunday before the last week of classes or finals week, depending on um, the way your classes work. In my class, we do one last thing during the last week of class so that I can leave you with more things that you've learned or at least encountered is my plan. Okay. So you can see here I've got the 16 projects yet to do, and those will take a while, so I will do my best to get them to you as quickly as possible because um, I know people don't, they get antsy if they don't start getting results back. Okay, week 11, right? Yeah, week 11. So what we're doing is we are adding more algorithms to the linked list we started last week. One of the reasons why I was able to get all of the labs from last week graded is because a lot fewer people turned them in, which is fine. I assume people are taking advantage of the sort of freebies that I give by dropping 2 weeks of work. So that's a good use of those that forgiveness is during a project weekend. But you do want to go back and do that lab because that lab is building blocks for this week's lab, which is building blocks for the third project. So let me walk through the module before I do anything else. So we're going to add code this week to free all the memory of a linked list, to remove the first node from a linked list, and to deallocate the memory associated with a linked list when it passes out of scope. So we have some to talk about, and I will draw some pictures which I do my best. It's the best way for me to hold my flow, and hopefully you can read and understand the pictures if I don't make too much of a scribbly mess out of them. One reading for the week was just about how and why do we use linked lists. For you guys, the linked list is the building blocks of the next many, many data structures you will build in your career. So we are starting with the singly linked list. That's the most sort of basic of the dynamically linked structures. Our second project will be a doubly linked list. Our fourth project will be a binary search tree, which is a variant of a linked list. If you go on in computer science, you will build graphs, which are variations on linked lists. You will build different types of trees, which are variations on linked lists. So this work on learning how to make a linked list and understanding how to use dynamic memory and pointer syntax, it's critical. You're going to be using it a lot for a long time in computer science and beyond. All right, Lab 11. Let me go ahead and open that, and then I'll come back to it. I'm more or less going to redo all the kind of walk back through all the algorithms for this week just to make sure that you've heard it twice, at least from me. The discussion is one of those that's not too difficult, I hope, which is go out and find where people in the real world are making software using particular applications of linked lists, in this case, stacks and queues. Project 3, I will open that, and sorry about this in advance, but I will pester you about it because the day to start this is not on November 20th, and I don't care if I'm preaching to the choir here in the lecture or but maybe there's one person who will get a better habit about this, so it's worth saying. Today, the day to start Project 3 is probably yesterday, but let's assume that you were busy polishing off Project 2. So the day to start Project 3 is today. Read it. Pay attention to what the labs can do to help you solve it. Work on the things that you already know how to do. There's a file parsing component here. So you already know how to do that, although this one is a little bit different in terms of the data and the formatting of the data. But you basically know how to do it, so you can begin on Project 3, even if you don't have the linked list prepared for it. So sorry about that, but I have to mention it because I'm hoping that someone who isn't in the habit of starting early will get in the habit on this project cycle. Wait, that's next week's goals. Oh yeah, I was already on the reminders page. What am I doing? Lab and discussion as always. Project 3, the reminders always have the next project on them because the time to start them is always now. Always the moment when you're not already working on one. Okay, so that's that. The lab this week is expecting that you completed the lab last week. So if you did the lab last week and it went well for you, then you will be happy because you can just add more stuff to that same code base. If you didn't do the lab last week, then I guess I would argue you should be happy because you now have a chance to go back and get that experience if you didn't have it last week. So much of it is literally the same functions that don't have to be touched again. Even though I'm going to talk about them again and build a linked list from scratch. So I'm right now just taking stock of what we've got. A node with a constructor to string, clear, empty. Clear removes them all, empty checks to see if it's empty, get the number of nodes in it, get the item at the front or throw an exception if there's nothing there. Remove the item from the front or throw an exception if there's nothing there. Add an item to the front, which means create a node and connect it up. And then a destructor, which is kind of the big new thing. So we really have two new algorithms on the list, which is clear and pop front. And then one new concept, which is what does a destructor do? Okay, so first destructor, and then we'll do the algorithm part. 21, this is week. Wait, yeah, this is week 11. Good news. Because we don't have just tons left. I'm just looking at the feature. Oh, this thing. Okay, so let's just start with this. Let's make a little class for ourselves. Now I'm going to want strings, and I'm going to use the catch-all using directives so I can save space on the screen, even though I don't consider this to be the best practice. For demonstration purposes, I want to save. I don't want to clutter up my screen too much. Okay, so this is a, oh, it does. Yeah, let's use a class. What the heck? So we'll just say that it has a contents in it, and we'll say that it has a width and a height and a weight, just for the heck of it. And then I'll take advantage of this as an opportunity to do some review. Ooh. In fact, I'm going to do this. This will be a lot more entertaining. In fact, let's make this one a struct. What the heck? Okay, and this will be string name, float, weight. Those are the contents part. And we'll make the box just be the contents plus a width and a height. So we'll get a little bit of bonus material in here. But I also needed some dynamic memory going on. So this is my setup, and then I will explain my setup, and then we'll add stuff to it. So I have created a struct called box contents, which will contain a string that's the name of the contents, packing peanuts, weight, almost 0. Why a struct? Because it's just 2 data fields. I want to show you a struct in this context also, but also because I don't imagine that there's going to be any fancy algorithms associated with the box contents. It's just going to be a thing with a name and a weight. That's it. So I'm just going to take advantage of the fact that structs already expose data members public by default, which is going to make my coding of them a little bit more convenient. The box is a class, in part because I want you to see a struct and a class kind of working together in the same context, and also because it's possible that I'm going to end up adding a few algorithms in the class box. And to me, whenever I'm doing kind of fancier algorithms, I use a class even though I don't have to. So don't forget, struct and class are pretty much interchangeable. But for my purposes, a class immediately kind of brings to mind something that's a little bit more elaborate. It's got more functions in it. It's probably got some algorithms, some memory management, some things that are beyond just some data fields. Yes, okay, so Emberwolf asked if I move the struct to the confines of the class, what happens to the public-private thing? So we'll explore that idea when I move it over. So you've anticipated one of my near future moves, Emberwolf, which is I'm going to take the struct definition and embed it in the box. And then at that point, we'll see what public and private does to us. So it's a very good question. And hopefully, and if I don't, please bring it back to me. Hopefully that question will be answered. So the question is, if I were to embed the definition of box contents within the class itself, does that kind of eliminate the meaning of public versus private? So we'll see by doing an experiment here in just a moment. Okay, so I have a class box. I am going to make a default constructor, and I am going to make an overloaded constructor where I can supply. Oh, no, let's just do a default constructor. That's it. we will make a add box and then deal with the problems associated with that. For starters, I guess we'll just say, yeah, so let's go ahead and just do it all the way. Add box, remove box, and I'll just kind of build the whole thing from scratch since we don't have a whole lot of link stuff. Okay, let's just do it that way. So we have the struct for the contents. We have the ability to pass in a pointer to contents, which will become the box's own contents. And then we have the ability to eliminate the box itself. So now let's kind of wire some instances up. So let's make a box, B1. So I'm going to make a static box, which means the box itself, I don't need to worry about new and delete or any dynamic memory issues. But the reason why I'm setting it up this way is because potentially the box is going to become responsible for something that's dynamic inside of it. So now let's make some contents. And anyway, I'm going to do everything kind of just brutally from the most basic level and then improve upon it over time in the hopes of explaining why I'm doing what I'm doing. So that keyword new should be setting off alarm bells for everybody. Because that's dynamic memory, and this means that we need to delete somewhere. And then I'll go ahead and it's a pointer now, so I'll go ahead and set its contents to be packing peanuts, and it's right. Oh, name. Oh, that's fine. Weight. I don't know. Let's say like a, well, let's say quarter of a pound, 4 ounces. And then I'm going to be making improvements as I go. And I haven't forgot about the struct thing. That's one of my improvements. So I'm going to make improvements as I go, and hopefully you can keep up with me as I do this. So this is a perfectly fine way to initialize a dynamic instance of box contents. But I'm kind of unhappy with having to write 3 lines of code just to build a box contents with the name of the stuff inside and the weight of the stuff inside. So what I'm going to do to improve this is I'm going to go to box contents itself, and I'm going to make a constructor. And I'm going to use the constructor to initialize the name and the weight of the box in question, which is what this part is about. So structs can have constructors, and sometimes it's handy to do that simply because in other places in your code, it eliminates nastier looking code for prettier looking code. Now I can build the new box contents. Packing peanuts. So why did I write a constructor in the struct? Simply because I knew that I would like to create these things, and I believe it would be a little bit more convenient over time if I have a constructor so that I can build box contents in one line of code. So that's all the constructor did for me here is I offloaded the extra lines of code into a constructor so that now when I make box contents, one line of code. So that's my first improvement, is I put a constructor in the struct, and since they are effectively the same as classes, there's no harm in doing that at all. and it's a convenience to save me lines of code later. That's it. All right, so what do I do with this box contents? Well, I'm going to add box contents, which is unimplemented right now. I need to go implement that. But what I want to be able to do is simply connect this BC1 contents to the box that I want them to be stored in. So let's implement this, but separately, shall we? So outside of the class, we will say void box, add box contents, which isn't an actual box contents, it's a pointer to one. And then I will say this contents equals contents. So now I have placed a dynamic contents into the box. And what I'm hoping you're going to see pretty quickly is that this is kind of getting hard to read already. It would be easier for us possibly to keep track of if I separated it out. So we'll see. For now, I'll just kind of do this box. And then I'll do the same thing below the implementation, so that at least we can kind of see where the box code begins and ends. So Magenta asks, why did I implement the function add box contents outside the class? Generally, it's better practice to do that. And I can give you the technical details, but one reason is because you want to get in the habit, because I'm going to require it of you sometimes. You want to get in the habit of recognizing code when people have separated the implementation from the declaration. So there's the declaration, and here's the implementation. So I want you to get in the habit of seeing it written this way, because that's commonly how this is done. People will have a header file for the declaration part, which anyone can read, and this should be all you need to see to actually use code, is the header file. The details of the implementation don't matter. So very often when people are distributing libraries of code, they will distribute readable header files. In fact, always they'll distribute readable header files, and they will distribute compiled implementations that you can't read even if you wanted to. The reason why they would distribute compiled implementations is to protect the copyright of their algorithms. So they don't want you to see how they did it. So that's commonly why that would be done, is to make it so that people can't see sort of the copyrightable details of an algorithm's implementation. So there's that. The other reason why you want to be in the habit, when you can, of separating them out is that if you embed function implementations in a class, it creates bigger compiled files. And you would rather have smaller compiled files often. So this is good practice in part because you can make smaller and then unreadable compiled versions of the implementations part of the code. So I hope some of that made kind of sense. I want you to know how to read it this way. I want you to know how to write it this way, because people write it this way so that they can distribute readable headers and unreadable code to protect their algorithms. And also, they can distribute readable header files and much more efficient and smaller compiled libraries of the implementations part. Okay, so there's that. And let's go ahead and do remove. Well, let's go ahead and do remove box. Even though I'm going to leave it blank for the moment. I don't have the constructor yet either. So let's get the constructor, which is really just about I'm going to have an overloaded constructor. Contents will be null. And then I guess the, we'll just make the width height. Oh, no, the weight is part of the contents. Okay, so there is a default constructor, which this box now has. We want to make sure that we null things out to start. So the default constructor is a good place to do that. I know that modern C++ has a different way that people often do this, but I want you to also be in the habit of understanding what's happening when. So understanding that this default constructor fires when I declare this static box is important. If in doubt, by the way, put a print statement to prove it. Okay, so this code's starting to be hard for me to look at because I'm having to scroll up and down. That's probably causing you problems, which would be another reason to separate it out for demonstration purposes, as long as we don't lose track of what we're looking at. So there's the implementation of the 3 functions that I have declared in the class box. A default constructor, a function to basically set the contents of the box to some probably dynamically allocated contents, and then remove box contents, not the box itself, which doesn't make any sense. For a box to remove a box makes no dang sense, unless its contents is a box, I guess, which I haven't implemented yet. Okay, so static box. Why is static important? Because the memory for the static things is cleaned up automatically. Dynamic box contents. Why is that important? Because it is not cleaned up automatically. So let's go add some proof of some of these things. So let's start with the easy one. See, this thing is getting so hard to read. That's fine. That's fine. Okay, so before we do too much more cleaning up to make things a little bit better, let's go ahead and add the new thing, which is a destructor. So destructor is a special function. It's the name of a class starting with a tilde. Destructor's job is to do cleanup on instances of classes when cleanup is required. So for starters, I'm just going to implement the destructor while I get rid of the contents in it, by the way. So let's start simply by implementing this destructor. Kind of looks a little bit, I don't know, makes me think of Botox. So scope resolution, the function has a special name. And then we will use an output statement to show us when destructors are happening. So nothing else in main right now other than the default constructor, which will print the message and then do some zeroing out. And then what else? We don't know. So there's the constructor because I created an instance of a box. There's the destructor, even though I didn't do anything. So this is hard. Why is this destructor happening? Does anybody know why the destructor is happening? And if you don't, I'll set it up differently so you can get a different look at it. All right, so let me set it up differently and we will look at it. So let me make a little it's not a bad guess about the function being. So that's true, Emberwolf. You are correct that the reason why the destructor is firing off is because, well, I implemented it, but I think maybe what you're getting at, which is correct, is that the destructor somehow is automatically happening. And this is important to note. Destructors only ever automatically happen. You should never, ever, 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 ever call a destructor in your code. And I will say this, I hopefully on multiple occasions so that when people do it, I can say something to them in their own code about it. Don't ever call a destructor. You let that behavior happen automatically or sometimes semi-automatically. And I'll show you what that means in a second. So let me change the setup and let's see if we can make then more sense. So we'll call it box maker and I will make a box. That's also a good guess, Magenta, but no, it doesn't have anything to do with null just yet. So let me do this. Let me put an extra line break here. In fact, let me just get rid of these and use line breaks. Okay, so I want you to notice my little different setup. The program's going to run. It's going to print starting program. It's going to call boxmaker, which declares a static instance of a box. So we'll see what happens. And then ending program. Okay, so what is going on that a box is made and then a box is destroyed? So you're close, Isnam. You're very, very, very close. So this calls, so line 51, so the answer is something about these things being called automatically, and that is correct. In C++, it is hard sometimes to see constructors when it's the default. So line 51 is using the default constructor, and we can actually see that because the default constructor prints a message. Now, something about that word automatic is happening here in this program. Something automatically is happening to call the destructor in this program. So start constructor and destructor fire. It's not quite the same name, but you guys, I think, are kind of getting around to getting closer at it. And then ending program. So maybe we'll go at it this way. Does anyone, what do we call a variable that we declare inside of a function like this? So if you think of box B1 as a variable, what kind of a variable is it? Local or global? That's true. It's a static variable. So that's Isnam. It's a static variable. Is it a local variable or a global variable? It's a local variable. All right. So a bunch of people got that right. B1 is effectively a local variable. So what does that mean? It means that the variable is created when the function begins to execute, and then it is released or destroyed when the function stops executing. So that's right. Emberwolf said it with the perfect terms, which is where I was hoping to get to. So box B1 has a scope that's limited to boxmaker. So box B1 is created in the scope of boxmaker and destroyed in the scope of boxmaker. Creating B1, I had to do. Destroying it, I didn't. When the program left the scope of boxmaker, B1 was automatically destroyed, meaning box's destructor was called. So in the scope of this function, B1 is created because I created, and destroyed. The destructor is called automatically when it passes out of scope. So this happens all the time with variables. They're created for a scope and they're destroyed when we leave the scope. And it's true for objects as well. And we can actually see it happen with objects because they have a destructor that's automatically called to destroy them when we leave that scope. It's very, very handy, as Emberwolf points out, because it gives us a chance to do things like manage memory. All right, so now let's watch this. I'm going to make it dynamic instead. And we'll see what happens. That's true. So Magenta asks, I mean, if we create a box object in a function, and it only exists in the scope of that function, then if we needed that box elsewhere, we would have to return it somehow. And the answer is yes, that's correct. Okay, so now let's run the program again, but let's do it with a dynamic box and see what happens. Okay, so what's the difference with a dynamic box versus a static box? It did not destruct. That's exactly right. So in C++, when you use new to dynamically allocate something, it will not auto-destruct for you. It has to be destroyed. So the way we would do that is delete B1, which will cause the destructor to fire off. So there's goods and bads to this. This is a reminder that if we use the keyword new, the thing that we created with new is not going to get destroyed for us. But if we come back and use delete, then it will fire off that destructor. So now let's thicken the mix a little bit. So let's have it return a box pointer. And while I'm at it, I'm going to introduce you to a concept. So this B1, if this function is just here to make a box, this B1 doesn't actually do anything useful. So why not just get rid of the middleman and just return a box? We don't need the label on it. So this is an anonymous object. It has no name on it, but it does exist. So in the context of this function, it does exist. So now let's use the function and capture that box. And then run the program and see what happens. So we're going to use an anonymous box object because in the scope of the function, we don't care if it's labeled or not. It's just a dynamically allocated box. In the scope of main, we'll go ahead and put a label on it so that we can do stuff with it. Okay, so the destructor didn't run. So the question here is, what's missing and where do I add the missing piece? I need to delete it. This nom is exactly right. So where should I delete it? Should I delete it somewhere up here? Or somewhere else? So should I delete it inside of after the return? All right, so exactly right, Emberwolf. The caller in this case, which is main, since it wants the dynamic box, it needs to take responsibility for cleaning up after it. And let's do that after the ending program just for fun, just to see what happens. So you're going to see this a lot. You're going to see functions that create dynamic things and then expect that other functions will clean them up. This is a common source of memory leaks because it's very easy to forget that the function is not going to clean it up for you. The function makes the box for me, but it's not going to remember to clean it up. In fact, it can't. So I got to clean it up for myself. Lots of memory leaks happen because of this. This is one of the reasons why some languages have garbage collectors. So let's run it, and we will see that the destructor happens after the end of the program because that's when I deleted the dynamically allocated thing. So these kinds of things are not easy to deal with. All right, so let's go ahead and do the same experiment with the box contents. So I'm going to go ahead and put a destructor in box contents only for the purpose of noting when it executes. So let's see if structs do this same thing. And then we'll try to get at why am I doing all these kind of weird layers, and isn't it starting to get confusing? And the answer is yes, it is. All right, but we are keeping track of, because we can see it, but we can't always see it. Box maker makes a dynamic box, but doesn't clean it up. So I need to make sure that I do deal with that problem here. Okay, so now next two steps. Let's put the box contents back in there. So let's make sure we don't delete. Let me move these things down to the actual end of the program now. Okay, so here we go. We have a dynamic box. We have a dynamic box contents. We add the dynamic box contents to the dynamic box, and then we delete the dynamic box. Let's go ahead and put a print statement in box contents so we know when it's constructed. And I'm going to go ahead and do it all the way. And I'm running out of space, so let me wrap it. Right? I think that's right. I'll put 2. Okay, so now when a box contents is constructed, we'll know it. Now when a box contents is destroyed, we will know it. Now when a box is created, we'll know it. When a box is destroyed, we'll know it. And then in our main, we use a function to allocate the box. We just go ahead and make the dynamic box in main. We add the dynamic box in main. We end the program, and then we clean up after the dynamic box. So dynamic box with new. Dynamic box contents with new. Delete box. So hopefully some of you are already guessing. Oh, shoot. B1 is now a pointer. All right, so there's the box being made. There's the contents being made. There's the program ended, and then there's the box being cleaned up because I deleted it. I need one more delete. Good one, Ember Wolf. So I need one more delete, which is this BC1. So BC1 needs to go away when the box goes away. So let's see what happens if I delete BC1 after deleting the box. Okay, so that worked out okay. But let's think about this at a higher level. So if we make a box for the purpose of storing contents and we throw out the box, we kind of want the contents to go out, or we ship the box, let's say, by deleting it. But we want the contents, so goes the box, so goes the contents. So in other words, what we'd really prefer is when we delete the box, we delete the contents that are inside of it. So Magenta is got one of the necessary steps here that we need to null the contents. But the way to do this often, if we want the contents to go when the box goes, in other words, deleting the box should delete the contents, then what we do is we go to the box destructor and we say, hey, box constructor, clean up after yourself. So one of the cool things about these destructors is that if you have one object that contains dynamic other objects, you can use the container objects destructor to delete the content objects that are dynamic. I hope that makes sense. So when we delete the box now, that calls the box destructor, which deletes the contents that went with the box. So probably for most people this is making mostly sense right now, but when you sit down at code later it won't anymore. At least that was always my experience. Like, yeah, got it during lecture, and then I'd go home to work on a lab or a project and think, I don't get it anymore. So I know that that is a frustration that many of us experience. It's really just practice, exposure. The more times you do it, the more your eye will begin to recognize, and kind of your brain will be able to manage the varying layers of things. Yeah, so Emberwolf and Magenta are having a similar experience to what I had, which is I hear it in lecture and like, yeah, that's perfect, and then come back a day later and like, I don't know what any of this is anymore. So yeah, I get that. I wish there were any way to kind of fix that other than experience, but I don't know of one. Okay, so hopefully though it kind of makes sense that delete the box, delete the contents. That's what I'm doing here. Let's run it, make sure that that's true. So we didn't have to delete the box contents separately. We let the box delete its own contents. Now let's do something naughty. Let's see what happens if we just eliminate the existence of the contents from this box. Let's see if the program does anything different. It didn't, so that's a relief. But it could, so we need to deal with that at some point. Okay, so box contents, we put it in a box. Oh, yeah, I can refactor this, by the way. So why not just eliminate the middleman? I don't need the label BC1 to do this. I can just use an anonymous dynamic box contents and get the same result with less code. It's kind of weird to look at first, but if you see something like this hanging around, that's an anonymous object, meaning it has no label associated with it. Although once I go to box contents, I will realize it does have a label. It's labeled inside the box. Should be the same at this point, although it will get cleaned up for us. Okay. So destructors, we'll keep this in mind, and I'll repeat this over a linked list example. And also I've been kind of refactoring and showing you anonymous objects because it could. Yeah, let's go do a little bit more cleanup here. So we want to be kind of paranoid in our code when there's pointers around and try to root out all of the null ones. So the problem of remove box contents would be to delete the contents and then null them out. So this is what Magenta said. We need to make sure when this is appropriate, we need to do it. So removing the box contents is simply deleting them to null them out. Deleting them and then nulling them out. But we need to also do a little bit of paranoia here. In fact, let's see if I can cause the situation to happen. So let's add a function to the box. And I'm going to be lazy here and just call it test print, because I don't want to do toString and spend time on that at this moment. So test print, which will be void box test print. And then we will say Ooh, I'll make a little box and put the contents in them. That'll be slick. All right, so box with contents. Let's do that right after we add some contents. Let's do it before and after we add contents. B1 test print. Add some contents. And then B1 test print again. And let's see what happens. So what I'm trying to expose you to here is just the different things that can happen at different times. So for now, we're going to make a dynamic box. Technically, it doesn't need to be dynamic, but let's leave it. We're going to test print it to see what that looks like. We're going to add, using this sort of anonymous style of creating a dynamic object, we're going to add some contents, and then we're going to test print again. Then we'll end the program and delete the dynamic box, which will handle itself the problem of deleting its own contents. All right, so let's see what that looks like, though, when we run it. All right, so here's the first one, box 0, and then box gobbledygook. So I'm doing this so that you will make note of this when you're writing your own code. If you see gobbledygook, what it means is you printed the pointer, not what the pointer points to. So this 0x1EA22E0 is an address in the computer's RAM. And that is the address of where the box contents were allocated. So that's a RAM address, and that can be useful information, but that's not what we wanted. We want the actual words that are the box contents. Yeah, it is awesome, Emberwolf. I agree. So Emberwolf's saying that's pretty cool that you can do that, and it is cool. The box 0, by the way, that's when it's null. Okay, but we don't really want the addresses, do we? Can you print that on the terminal? No, I don't think there'd be so Emberwolf is asking, can I use this on the terminal somehow to get into RAM? And no, I don't think the operating system will let you do that. The operating system's kind of protecting this area of memory that the program's using. It would be cool. You may be able to get a debugging program that can access the computer's RAM and do that. Okay, so yeah, we printed pointers, not the stuff. So let's print the stuff. So this is going to be one of those. I have to remember what contents is. Contents is, it's a pointer to box contents. And if I go to box contents, then I can get the name and the weight if I want it. So I'm going to get both. So this is a pointer to this kind of the box's pointer to itself, getting its contents, which is a pointer to a thing with a name in it. And then I'm going to put a comma here. And let's go down a line. And we will go get the contents, which is itself also a pointer. So I will get the weight and I will dump it right there. So there is the box. So I'll print the contents' name, which is a chain of pointers. This is a pointer. Contents is a pointer. And then I finally can get from there to the name. I can do that to get to the weight as well. Okay, so what does that show me, though? It won't show me. It will crash, which is what I wanted to happen. So thankfully it did happen. It will crash. So what's the problem with the crash? So notice that it crashes. It makes the box, and then it crashes when it tries the next thing. So what's causing the first null pointer? That's exactly right. So there's a null pointer in here that's causing a problem. It's causing it to crash because And I think it was Emberwolf said it. That's correct. To start, the contents are null. And if the contents are null, well, you can't get from null to a name. You can't get from nothing to data. So we need to be paranoid here and make sure that it's not null. And I'm going to go ahead and do an else. And I'll say cout box empty. So we got pointer stuff going on. We need to start being kind of paranoid that the pointers are possibly not null. So we should get an empty box first and then a non-empty box, we hope. So there's the empty box and there is the non-empty box where we chained the pointers to get to the name of the contents and the weight of the contents. Okay, so now let's do this. See if that still works. I keep putting T in there. Remove box contents, wrong function name. Okay, so far we're still okay because of that null check. But let's go ahead. Yeah, good one, Ember. Yeah, that T. Okay, so being paranoid about pointers when we are using them is a good idea, even if it does not seem to be causing any problems. Here's another place where being paranoid would be a good idea, or possibly throwing an exception. So let me get exception handling in here. What ones does the lab want us to use? Logic errors. All right, so we'll do the same thing here. So this might be a good time to start thinking about exceptions or null checks. Depends. For you guys on your labs, it's going to depend on what I tell you to do. So you don't have to puzzle this out. If the function says throw an exception on a null pointer, then you just do that. All right, so this tells me I should be throwing an exception. So if those contents are null, then we need to throw a logic error. No contents, we'll say. Else, safe to delete. And we should now get that. When do I throw? Yeah, so Emberwolf is asking, when should I throw an exception versus when should I just handle it in a different way? And there's no hard and fast rule. There's a lot of debate about this kind of thing. You kind of, when you're deciding whether or not to just handle the errors with an exception, which are pretty harsh and dramatic, or not, you tend to think of how severe the error is in terms of your program state. So generally speaking, like in the case of test print, I think it's okay in this case to just say the box is empty, and that's probably adequate. We don't need to crash the program around it. But if you're trying to remove non-existent box contents, then I'm just kind of making my judgment that I want your program to crash so that you're aware that you're doing that. Or I want you to sort of put more work into handling the problem of trying to remove non-existent contents from a box. So it's all a matter of judging how severe you think the problem is. Um, and really all this, the way you do this, exception or otherwise, um, kind of affects the people who use your code. So, um, and I'll show you what I mean by that. And so you kind of decide how much work do you want the people who are using your library to have to do to deal with these situations for themselves. So I'll just give you an example. Remove box contents throws an exception, but as the sort of user of the code, I'm not dealing with that right now. So what happens? Oh no, I need to remove box contents twice, don't I? The second time should be a problem. Yeah, so this is kind of the idea. Um, the first time someone uses your code that does one of these sort of more serious errors, your program's going to crash. And some of us think that we want to make programs crash when people make serious mistakes and force them to deal with it better. So by throwing an exception here, I am forcing the people using my code to work harder to deal with this problem for themselves, if that makes sense. Because if they don't, the program's going to crash. So how then do I deal with this as the person using this code? I embed which this won't go back. I embed these in try-catch blocks. So because of that exception, I am forcing another programmer to kind of take this extra step to deal with this problem more officially. Anyway, it's all judgment, it's all experience, and there's still even people have different opinions about how and when to use exceptions. I'm getting you guys in the habit of using them for kind of severe null pointer problems, which would be I'm trying to access an element in a collection and the collection's empty. Well, to me, that's a fairly severe problem. Like you're trying to access stuff in an empty collection. I want to draw your attention to that and force you to deal with it in your own code. Whereas if you're just saying print out the collection for me and I just kind of put on the screen, hey, there's nothing here yet. That's my judgment. So I wish I had a better answer about that. It's a matter of opinion. It's a matter of experience. And it's a matter of how much work do you want to force the people using your libraries to deal more carefully with some of these situations. And what an exception will do is that if it's not dealt with, it'll crash the code. And sometimes you want that. Sometimes you want those other programmers to experience their program crashing while they're in development so that they are aware of that situation and deal with it effectively. If you don't throw an exception, then you may end up with people who are using your code and they are using it badly on their end, and the program just keeps running with garbage happening. So it's a matter of how important do you think allowing them to get garbage on their side matters. Anyway, I guess I'll stop talking about it with that. So anyway, the exception kind of forces me on the calling side to deal with this code more effectively. So here we get the no contents exception. So the program doesn't crash, but that's because I forced myself to be more careful on both sides, by the way, on both sides. So I like exceptions for those kind of, boy, you try to do this and that's a null pointer. That's not a good thing. And I'm going to make sure you know about it and deal with it. Box contents. So in this case, here's an example where I think, well, I don't think that's that big a deal. There's two ways to deal with this, but let's just say If I've already got contents and you're trying to replace it with other contents, well, I'm going to go ahead and just clean up before I replace these things. So in the case of add box contents, it turns out that the problematic situation is you're trying to put contents in here with the box that's already got them. So what I have chosen to do here is just delete what I already have as contents and null them out before I take in the new contents. I could, if I wanted to, throw an exception here saying, hey, you're trying to add contents to a non-empty box, and that might be a good idea. I can't decide. In this case, though, I'm just going to quietly dump their old contents, but this also kind of, I hope you can see, the programmer on the other side, there's nothing to tell them that I just deleted their old contents, and there's no way that they're ever going to know that happened unless they were paying attention. So sometimes you think to yourself, maybe I should throw an exception here so that they know, hey, you're trying to replace contents in a box that already has them. Well, there's no, so the question in chat is there a way I could give them a warning? Not really. I don't want to put user interface in here. That doesn't make sense. I have no good way of giving them a warning. Now I could do this. I could say, so I could give them an extra tool to check for themselves, right? So then they could say, if not B1 has box contents, then it's okay to add some. These are good questions you guys are asking. So here's one way I can sort of offer some assistance to the people using my library, but they have to do this, right? So there's a function there that you can check, but if you don't check it, then that's on you. And that's an okay way to go about it as well. You have all these decisions when you're making this kind of code. Like I'm storing collections of things, or even just a single box with a single contents in it. And suddenly I have all these potential problems. Like, well, what if they want to replace the contents and they don't know there's already contents there? And what if they want to remove the contents, but there aren't contents there? It sort of brings up a lot of possible places where you're compelled to make decisions. So you just kind of have to choose. Some people might kind of lean toward more dramatic interventions, like throwing exceptions, which will cause the program to crash until they deal with it better. You might deal with it by giving them an extra function that if they choose to use it, they can prevent the errors themselves. Or you might simply just silently go about your business and they better just do it right. Up to you. But yeah, it takes practice and kind of knowing the people who are using your libraries and what their preferences are as well. It's kind of a lot of stuff, isn't it? Okay, so there's a lot. Here's another place, by the way, in the destructor, probably a good place to make sure that we have contents worth deleting before we delete them as the box is being deleted. So we'll just make sure, are there contents? Okay, safe to delete them as the box is passing out of existence. So let's see, destructor is now checking. Add box contents is now checking. Has box contents, that's what it does, is check. Remove box contents throws an exception after checking. And test print also checks and changes its output. So it's a whole bunch of different ways to go about that. On the lab, I have dictated to you which style to use. You can store these things in a file, yes. So we could open a file and write these things out if we wanted to. Beyond our scope with my time running out, but Magenta, if you can remind me of that, I'll try to put it in my notes for next week. But if I forget and you can remind me, I'll try to work that in somewhere. Okay, before I go look at the lab, let me do the one last bit of refactoring I was going to do here, which is this this box contents. So the question came up, could I take the box contents and simply embed them where that term is being used in the code itself? And the answer is yes, I can. So it's a little weird looking at first. So I've taken the entire struct definition. I need to take that semicolon out. I've taken the entire struct definition, have moved it inside of the class. I've left its destructor actually and its constructor. And now made just declared it right on the back end of its own definition. This is how we do it in our labs for now. So can I do that? The answer is yes, I can do it. Now it does change something because I can no longer add box contents in this way. So now that box contents is defined within the box, I can no longer create instances of it in main. So what I would have to do in this case is I'd have to tell the box, hey, I need you to make some contents of packing peanuts and a 1/4 pound for me. So the box is going to take on the job not only of deleting its own contents, but of creating its own contents. So the way to do that, add box contents. Where did it go? Oh, here. So it won't be this version anymore. It's going to be this version. So now the box itself creates its own contents, or at least that's what we're going for here. Let me do that on the next line after. So these layers of indirection can be very, very off-putting. Yeah, these do look a lot like what we do in Go. So yeah, we have this indirection now because main can't create contents for itself. It has to go through the box. So it has to ask the box basically, will you please create these contents for me? And the box will then create the contents. So now let's see if this runs and then see if we have, oh, the public private thing. So if this were a class, I think it would still work. It doesn't. So check it out. Box contents. So as a class, its data members are private, and even though it's defined inside of the box can't access box contents data members directly. So this goes back to that way earlier question, like, doesn't this just kind of erase the whole public-private problem? And the fact of the matter is it does not. A class, everything is private inside of it, even if the class itself is defined inside the context of another class. So if it's not a struct, then we would have to do a whole bunch more work, even though we're inside of out of line definition. What has box contents? Oh. Forgot to put a header for that. Okay, there we go. So yeah, even though we've now embedded it within the box, it still needs to be a struct, or we still have to do the access labeling for it to work. So yeah, that was a good question. I'm going to share this whole REPL so that people can go later say, what in the heck is all of that mess? Hopefully not. Hopefully I left enough breadcrumbs behind that you can kind of toy around with it a little bit. Okay, so I have 15 minutes. I apologize in advance because I expect I'm going to go over. Because I'm trying to do in one day what in a normal semester we do in 2 days of lectures. So sometimes I can be efficient and get through it pretty quick, but other times it takes me a while. So apologies in advance. Need to shift gears. I guess I can let chat vote if you want like a 2-minute break in here, or should we just proceed? I can let chat vote because some of you may want to get up and stretch your legs for a minute or two. But if not, then we'll just proceed. And then I'll wait and see if anyone has a vote one way or the other. And in the meantime, I will set up. All right, so magenta's okay either way. Lab 10. Lab 11. Lab 11. Okay, so nobody else voting. I'll just proceed. That'll get us done. Okay, so Edcast says proceed as well. So we'll just do that, and then yeah, that is what we will do. I'm going to set up the whole lab here, so I'm not going to share this stuff because it's the solution to the lab, but I am going to go and implement parts of it in the lab code itself. So let me set up for this. And then go get this stuff. So this is what? That's slist.h. slist.cpp, which is, oh yeah, it's nothing. And then main. Oh man, no. Is the unit testing stuff. I doubt I'm going to get to that in the interest of time, but I'll go ahead and slap it in here. Okay, so the unit. So anyway, here's the little struct that is defined in the context of the singly linked list. It needs to be a struct so that its members are public, even though it's inside of this other class. This is just a way to kind of, we only need this definition of the node in here anyway. So it's just a way of, kind of encapsulating the code. It's just one way to do it. It's got its own little constructor so we can create nodes as needed. Yeah, so that's that. We already have it to string, and we already have it is empty, which is really just return size is 0. And we already have a get size. We already have a front, I believe. We already have a push front. So we have a destructor, and we have a pop front. So, oh, and a clear, but clear and destructor can work together. So let me quickly do the push front just to remind you of why we need to do what we are doing. And if you see me make a mistake because I'm hurrying, yes, list, I think, was it spelled with capital S and L? It was. So push front. So we have a node star in equals new node. We need to use the constructor. This node constructor, which is embedded inside of the node class. Here it is. So all it does is null out the next thing, and it puts the value inside. All right, and then we connect it up. So node next equals whatever the head pointer points to presently, and then we can move the head over to this new guy, and then we can, what was the counter called? Size. Same algorithm as last week for push front. The reason why I wrote this is because of this new. So we know that the list is going to be dynamically allocating nodes, which means that it needs to free them. This is the only place where we could possibly do that, is because the list makes the nodes, it needs to delete the nodes. We're going to do that in two places. We're going to do that in the list constructor. We are going to do that in the list's clear function. And then I'm going to give you a hint. About how all this code's going to work together. So if we're clever, we don't have to write very much code at all to do all three of these things. So let's deal with the pop front algorithm, and then the rest of them are handled. And what I'm about to do is kind of consider all of the functions that I have available and then use them together with each other. Ultimately, I'm going to show you kind of the hard way to do it, and then I'm going to show you how we can do it so much easier if we just think about it for a moment. Pop front is supposed to throw an exception of the type logic error empty list. So I'm just going to copy that. So if this head is null, then we're throwing an exception. Okay, Amber, we'll see you next week. Thanks for being here for as much as you could. Okay, so pop front. The pop front algorithm is the whole trick. We don't want to pop empty front. So what's the algorithm? So I am going to switch over. It's 11:22. I'm actually going to be close to getting done inside of my hour and a half. I'm going to switch over and draw a picture. So pop front means we want this. I'm going to draw a couple of different linked lists. So we're going to try pop front on both of these situations. Doesn't really matter, but it's possible that one node is different from more than one node. Pop front simply means that we want to go from this to this. Right? We want to go from having one node to having no nodes in this case. In this case, we want to go from having two or more nodes to that one less node. So if I were to number these, right? So in this case, popping front means that we want this one gone. Get rid of it, which means we'd want this. In this case, if we want the first one gone, then we should end up with nothing. So that's what we mean by pop front. Remove the one that's on the front, but leave everything else. And notice, by the way, that in the case when we have two or more, this head pointer should shift over to the next one back. So I'm just going to do the algorithm, kind of show you where the problem is, and then we'll go implement it in the interest of saving time. So let's start with this one. All right, so if we start here, that's step 0. If step 1 were this, which is kind of what we wanted to end up with. But if we did step 1 this way, what ends up happening is that this node becomes orphaned. If we move this head pointer over, we lose track of this node, and thus we can't free the memory for it. So is the first move to move the head over, which is really head equals head next. So the answer is no, because we'll orphan a node and then we can't free its memory. So what about this instead? And this is, in fact, the way to do it. So what we'll do instead is we'll fire up a temporary pointer to point to this node, so that then in step 2, we can move the head over, but we still have temp keeping track of this one that we want to get rid of. So step 3 will be delete the temporary one, right? Which gets rid of that node, and then that's it. That's the algorithm. So I went fast, but I wanted to point out to you the reason why I'm putting this temp in here is because if I don't, I can't get this other page open again. If I just move the head over without tracking this node 10 here, if I just shift this pointer over, I orphan the one I want to get rid of. So I track it first. Then I can move the head over to where it needs to be second. So here's what that looks like in code. So to pop front, I am going to fire up and one thing that people get confused of here, temp is not a new node. I know that because there's no keyword new there. Temp is simply another pointer at something that's already being pointed to. So temp is just going to be used as a marker to what is presently the head node on the list. It's not a new node, and I know that because the keyword new isn't even there. Temp is not a new node. But that was that first step. Mark the current head with a pointer. All right, now the second step was move the head pointer over to the next one after it, sort of this little chain that gets me to the 20 node. So now the head is marking the 20 node. Now I can go back and delete the one that I marked for deletion. And also count down by 1. That's the whole algorithm. The order is important, and I recommend trying to practice drawing pictures of the order that you do things in. Because if you switch these 2 steps around, it doesn't work. You end up with a memory leak. You have to mark the current head with a temporary pointer. Then you shift the head over to the next node. Then you can delete the one that you marked, which is the front one. And then you can decrement the size. That's where all the hard work is. Once we've done all the hard work, then deleting all the nodes becomes very easy. So I'm just going to show you the easy way to do it, because clearing all the nodes is simply a matter of popping the front one until there are no more. Well, how could we do that? Well, we could say, while not this empty. So while I'm not an empty list, I'm just going to pop the front. So I'll just keep popping one and popping one and popping one and popping one until my own function tells me that there are no more left. Why develop complex algorithms when I've already done the complex algorithm part. Simply take advantage of the fact that logically clearing a list is no different from repeatedly popping the front one off until there's nothing left. Yes, so Magenta is asking, do I need to decrement this? And the answer is yes, for sure. You need to decrement the size counter because you have logic that depends on it. So yeah, every time you delete a node, the size should go down by 1. And while I'm not this empty popping, well, pop front is taking care of all of the work. It's going to remove the size by 1. And I will just repeatedly pop 1, it'll delete it, reduce the size by 1, and eventually the size will become 0, at which point I know that there's no more popping. And then I can use this algorithm for my destructor, because really the destructor just needs to make sure that the list gets cleared. So all 3 of those algorithms just work together. The destructor just needs to make sure that the list gets cleared. The list gets cleared is really just a matter of making sure that we pop nodes off the front until there are no more nodes to pop. And then finally, that allowed us to focus our energies on the one algorithm that needed to be developed, which is how do you pop that one off the front? So be on the lookout for this kind of thing in our labs for the rest of the semester. Can we use a function that we've already written to make our lives easier? In the case of clearing, we're actually using 2 functions that we already wrote. One is a check to see if the list is empty. If it is not, if it is not, then we remove 1. And we just keep removing 1 and removing 1 and removing 1 until it does become empty. And then we recognize that, well, deleting all the nodes is really just clearing the list, and I already have a function that does that. So there you go. That's that whole new stuff in lab. I'll leave it on the screen. Maybe I'll just leave it on the screen here for a few moments. Let me check my agenda. Yeah, so I'll just leave those as ideas because the discussion is going to touch on this anyway. So the discussion will be, okay, we've made a linked list, but do people actually use these in the real world in their code? And if they do, what do they use them for? So in the discussion, we will go out sort of as a group and hopefully discover that linked lists are used in a variety of different ways. And if you're clever about it, you'll discover people are clever about it and they have figured out different ways that they can use the functionality of a linked list to solve different kinds of problems. They're quite cool. Okay, so I think that's literally all the new functions for this week. And then you saw earlier I did the push front from last week, and then everything else is from last week. So if you're watching this and you didn't watch last week, we did those other functions last week in lab. So unfortunately, that means the best place to go get those answers is last week. And then put those in with this week, and then you've got a full working lab. If you did last week, then you are getting rewarded for your hard work because you are looking at everything that you need for this week's lab, I think. You will have a complete lab once you do these things. These are untested, so hopefully I didn't make a mistake, but if I did, we'll come together on Piazza and we will fix it. Okay, I think that's it. Thanks for hanging around. I only ended up going 3 minutes over. But thanks for bearing with me for the extra 3 minutes. Hopefully if there are questions, I'll wait another minute or two with that screen sitting there before I shut down. So have a great day. Have a great week. I will get the projects turned out to you as quickly as I can. Hopefully today before I go to bed tonight. All right. Thank you, Magenta. Thanks for being here. Take care, everybody. Have a good day. If you do things for Halloween, hopefully they're enjoyable.